In this lesson, we will look at logic gates. Logic gates perform basic logical functions and are the fundamental building blocks of digital integrated circuits. Digital computers use digital data in their operations. This form of data has only two levels of voltage. Digital circuits are two-state circuits. They are either on or off. The term logic gate refers to a switching action or actions. Simple mechanical switches can be used to produce logic functions, but in modern circuits the switching is done by solid-state electronic devices. Some circuits may have only a few logic gates, while others, such as microprocessors, may have millions of them. By combining thousands or millions of logic gates, it is possible to perform highly complex operations. Normally, when working on paper, we count from 0 to 9. This is the decimal number system. Digital computers use the on-off, two-state or binary number system. A full explanation of the binary number system is beyond the scope of this lesson. But quite simply, the only digits used are 0 and 1. Decimal 0 is equal to binary 0. And decimal 1 equals binary 1, but after that the two systems change. Decimal 2 is represented in the binary system by 1, 0. Decimal 3 by 1, 1, and so on, as shown on the screen. Logic gates take an input of one or more binary values of either 0 or 1 and output a single value of 0 or 1. You may find binary 1 also expressed as on, true, high, closed, or engaged, and binary 0 as off, false, low, open, or disengaged. In electrical circuits, the actual voltage levels required to achieve a binary 1 or binary 0 may vary, depending whether positive or negative logic is being used. If positive logic is used, a binary 1 equals a high voltage level, and a binary 0 equals a low voltage level. The actual voltage values may be either both positive or both negative, or one positive and one negative. The only stipulation for positive logic is that a binary 1 is created by a more positive voltage than a binary 0. Most digital computer systems employ positive logic. The negative logic concept defines binary 1 as the lower voltage value and binary 0 as the higher or more positive voltage value. Although less popular, negative logic is used in some systems in order to meet certain design parameters. Truth tables are a systematic means of displaying binary data. They illustrate the relationship between a logic gate's inputs and outputs. This type of data display can be used to describe the operation of a gate. There are 6 commonly used logic gates. They are the AND, the OR, the invert or not, the NOR, the NAND, and the exclusive OR gate. The name of each gate represents the function it performs. Each logic gate has a symbol of a specific shape. The purpose of the symbol is to specify the relationship between the inputs and outputs of the circuit, without the necessity to show the entire electrical workings of it. The inputs are always listed on the left of the symbol and the outputs on the right. We will look at each type of gate, beginning with the AND gate. Shown on the screen is the symbol for an AND gate. The AND gate is used to represent a situation where all inputs to the gate must be 1 to produce a 1 output. If any input is a 0, the output will be 0. The AND gate can have 2 or more inputs. We can build up the truth table for this 2-input AND gate by looking at all of the possible combinations of inputs and outputs. To help us with this, we can represent the AND gate by the electrical circuit shown here. The 2 switches in series represent the inputs, and the light bulb the output. With the switch open, it represents binary 0, and when it is closed, binary 1. If both switches open, the light will be out, indicating an output of 0. If switch B is closed with switch A open, the output will still be 0. Similarly, if switch A is closed with switch B open, the output will be 0. Only when both switches are closed will the bulb illuminate, indicating an output in binary terms of 1. Because all inputs to this gate need to be binary 1 to produce an output of binary 1, this gate is sometimes referred to as the all or nothing gate. The next gate we are going to look at is the OR gate. The symbol for this gate is being displayed on the screen. The OR gate may have any number of inputs. If one or more of these inputs is 1, then the output will be 1. The OR gate will only give a 0 output if all of its inputs are 0. A 2-input OR gate can be represented electrically by this circuit with the switches in parallel. If switch B is closed, or switch A is closed, or both switches are closed, the light will illuminate. Only if both switches are open will the light go out. This gate is sometimes referred to as the any or all gate. Spend a moment studying the truth table before moving on. The invert gate, sometimes known as the NOT gate, is represented by this symbol. This gate contains only one input and one output, and is used to reverse the condition of the input signal. It is most often used in conjunction with other gates. Electrically, an invert circuit can be represented by a switch controlling a relay, the contact of which is made when the relay is de-energized. With the switch open, position 0, the light is on, representing an output of 1. But with the switch closed, position 1, the light is out, representing an output of 0. As you can see, there is a very simple truth table for an invert or NOT gate. This symbol represents the NOT AND or NAND gate. Notice that it is the same as an AND gate apart from the small circle at the output. The NAND gate is an AND gate with an inverted output. The output of this gate will be 1 if any input is 0. This is the exact opposite of an AND gate. Here is an electrical circuit which will function as a two-input NAND gate. As you can see, with the relay de-energized, the light will be illuminated, indicating an output of 1. The two switches A and B are in series and are controlling the electrical supply to the coil of the relay. Only if both switches are placed closed will the relay be energized, causing the light to go out and indicating an output of 0. Here is the truth table for the NAND gate. Spend a moment studying it before moving on. Here is the symbol for a NOT OR or NOR gate. Like the NAND gate, this is the same as an OR gate, but with a circle added on the output. The NOR gate is an OR gate with an inverted output. This results in a gate where if one or more input is 1, the output will be 0. As with the NAND gate, the NOR gate can be represented by an electrical circuit containing a relay which is controlled by a number of switches. Only this time, the switches controlling the electrical supply to the coil of the relay are in parallel. With both switches open, the relay is de-energized and the light is illuminated, indicating an output of 1. If either switch or both switches is closed, the relay will be energized and the light will go out, representing an output of 0. Here is the truth table for the NOR gate. Again, spend a moment studying it before moving on to see the final gate. The final gate we want to examine is the exclusive OR gate. Here is the symbol for this gate. This gate always has two inputs and it produces an output of 1 when the two inputs are not the same. That is to say, for an output of 1, one input must be 1 and the other 0. The electrical representation of the exclusive OR gate is quite complicated, as you can see. You may, if you wish, spend a moment studying the diagram to see how it works. However, it is of little importance. The important thing with this, and indeed all of the gates, is to remember what the output will be with the various inputs. Here is the truth table for the exclusive OR gate. Spend a moment studying this before moving on to the lesson summary. Here is a summary of the main points from the lesson. The AND gate is used to represent a situation where all inputs to the gate must be 1 to produce a 1 output. If any input is a 0, the output will be 0. If one or more of the inputs to an OR gate is 1, then the output will be 1. The OR gate will only give a 0 output if all of its inputs are 0. The invert or NOT gate contains only one input and one output, and is used to reverse the condition of the input signal. The NOT AND or NAND gate is an AND gate with an inverted output. The output of this gate will be 1 if any input is 0. The NOT OR or NOR gate is an OR gate with an inverted output. This results in a gate where if one or more inputs are 1, the output will be 0. The exclusive OR gate always has two inputs, and it produces an output of 1 when the two inputs are not the same. That is to say, for an output of 1, one input must be 1 and the other 0. When you are ready, continue to see a review of the truth tables for the 6 logic gates. The truth tables for the 6 logic gates are now being displayed on the screen.